In the last video, we gave an introduction to TVaR and did some examples when our x is a continuous random variable, such as exponential, such as Pareto, such as log normal. I also mentioned in that video that when x is not a continuous random variable, strange things could happen, and our previous definitions, in particular 8, could run into some trouble. Okay? To see that, let's look at example 7. Let x be a set such that the probability of this set is 1 minus p. Let's define a special random variable is either 0 or 1. So basically what we have is 1 if something in A happens, otherwise 0. Right? Well, let's say if you think coin, you can let A to be tail. Then if tail happens, it's 1. Otherwise, it's 0. Right? Or if you consider a dice, you can let A be, well, let's say even numbers. Right? So if you throw a dice, if you get an even number, then you get 1. If you get an odd number, you get 0. So that is the meaning of this, what do we call the indicator function. Right? It indicates whether this set has happened or not. Now I want you to calculate TVaR. So, well, delta is something between 0 and the p. So of course, this is a discrete random variable. It takes two values, 0 and 1. 0 with probability p, 1 with probability 1 minus p. That's nothing but definition. And then, of course, you can easily write down the CDF. So anything less than 0 would be 0. And if my x is at 0, I will have a jump with probability p. And for anything bigger than 0, I can put greater than 0 down here. And less than p, less than 1. And once I hit 1, I will have full probability 1. So it's a very simple distribution. How about 1? So if the level is less than alpha, then 0 is the value, okay? Because it will be the smallest one dominating your level alpha. And at 0, we have p. So this alpha has to be less than or equal to p. Equal is fine, but cannot be beyond. Beyond p, I need to go to the next level, which is 1. And in order to get 1, my x has to be greater than 1. But for us, we know it's p is the separating point for the probability. So under the definition 8, if we take delta to be between this number, then we know if my delta is between 0 and p, my y is 0, right? And now let's say conditioning on x greater than 0. Well, then I can only take this point, right? So that's why, this is a simple but very good example. Here, I don't even need to do any calculation. If I condition on x is bigger than 0, strictly bigger than 0, the only possibility is 1. So my expectation would be 1, right? Because I don't have any other choice for strictly positive loss, right? It's just a 1. So it will be 1. Okay, so that's by definition 8. However, if you are going to apply definition 9, you're going to do an integral from delta to 1, right? Delta we know is less than p. So you're going to do from delta to p and from p to 1. We need to separate into two sub-intervals. That's because the first one, the integrand is 0. The second one, the integrand is 1. That's why I need to separate between them. And then it's easy to see the result would be 1 minus p divided by 1 minus delta. And this is obviously a number less than 1 because because my delta is less than p greater than 0. Of course, they are all less than 1. Okay, and then we have a trouble, right? Because we have two definitions for TVaR, they lead to different numbers. Okay, the first definition is bigger than the second one. So we need to do something, right? And we decide to work with this one. We think there is something wrong with definition 8. Why? It comes from here. Because what we want is, roughly speaking, when we define or when we consider TVaR, we want to know the average loss that is beyond the threshold, that is beyond the given VAR. So we want to do the average. So let me write it here. So we want to average over the worst 1 minus delta VARs, right? So here is the key. We want to average over the entire right tail, which has probability 1 minus delta. Okay, if my x is continuous, I will have exactly 1 minus delta, right? Because for a continuous random variable, any quantile level is achieved. So I have equality. But if I consider discrete random variable, it is possible that I will need to jump. If I jump, the level may not be enough, right? I want to do the averaging for 1 minus delta. But since I jump, okay, what I have may be less than 1 minus delta. Right? For instance, here, what I want is to do average over 1 minus delta. But since I jump, what I have is actually 1 minus p. So if I do averaging, what I do here is I average on the right 1 minus p probabilities of loss. But what I eventually want is, or what I originally want is, I want to average over 1 minus delta. Here, I'm using less than what I want. So we will need to compensate what is missing, right? What is missing? The missing part is delta is p minus delta, right? If we add those together, then I have exactly what I want. I want to average for the losses who they are the worst 1 minus delta percentage, right? Not 1 minus p. 1 minus p is somehow a little short, right, to what I want. So how are we going to make this up? That comes up to compensate for this special part, right? We, from this particular distribution, we know 1 minus p, the value is 1. Then if you want to compensate, you're going to move to the left-hand side, right? And the closest value we have is 0, right? So what would be your guess to compensate, right? So here it's we manually create this part, right? We assign 0 to p minus delta probability, and then we have this part as the right tail, which has probability 1 minus delta, and if you do averaging, you get this result, right? So for instance, 1, now the probability is no longer 1 minus p, it's 1 minus p divided by the entire probability, which is 1 minus delta. And 0 is something we manually edit. Then I have 1 minus p divided by 1 minus delta. This is exactly what I have from definition 9, right? So from this interesting example, we already know how to collectivify the underestimation for the probability, right? So what we exactly need is find the level. Okay, in the definition of VAR, we have to make this greater than or equal to delta, right? Of course, if you take equality, there's no issue. So which means, well, you can put, let's put equal. If If this is this, then it's perfect. Meaning we have exactly a loss such that the probability bigger than this loss would be exactly 1 minus delta. Okay, a problem happens when this probability is strictly greater than delta, meaning I jump. If I jump, then I will need to compensate for for what I jumped, right? So I need to compensate exactly this part of probability. Then, right, adding those two together is exactly 1 minus delta. That is the tail I want. I want to average over 1 minus delta probability. So that's what I want. But because I have a jump, what I get is 1 minus delta bar, which is less than this number. So I will need to compensate for exactly this level. Because by definition 8, I will need to do x greater than 1, right? That's not enough. This part actually leads to 1 minus delta bar, not 1 minus delta. So of course, if they are equal, there's no problem, right? This part simply goes away. The issue comes when it is not there, right? So we exactly compensate such probability so that we will have 1 minus delta as expected. Okay, I already explained this. With this in mind, then 8 and 9 are the same. So from this point on, we will always use this. Or okay, so we will not use the original 8. So we call this 8 prime. So if you have a discrete random variable, always use 8 prime in this course. Okay, that is my definition, and I will want you to apply 8 prime, not 8. Okay, unless I tell you so. So the default thing is to do this because then we have fully used the entire tail probability. So as usual, let's do an example to see what's going on. It refers to previous part of the question. Let me go back to example 4. So let me copy the distribution. Okay. So from example 4, I have this CDF less than 50.92, greater than or equal to 50, less than 80.96, 0.98, greater than 90, less than 100, and if x is greater than or equal to 100, my probability is 1. Okay, that is the most important information I get from example 4. Now let's solve this. Okay, let's start with 95. Okay, obviously we don't have 95, right? So 95 is between 92 and 96. So if I use 96, then I only use 4% tail instead of 5%. So I will have a little issue. So I will need to compensate for that part. Okay. So let me do it in 2 ways. First is use this definition. Okay. So I have 0.05. Between this level, 80 is enough. I don't need to write integral because it's a constant. So I directly write it as this is what I get from the integral, right? Still, let's do the integral first because it's from the original definition. So for anything between 95 and 96%, my VAR is 80, right? 80 is enough, dx or dy, plus the next level is from 96 to 98. Between this level, 90 is enough. And beyond this level, I will have 100. Okay, then you can easily do the computation. It will be 92. Now let's think. So this is definition 9. So let's apply definition 8. Apply. Okay. So VAR 95 is 80. Okay, and x greater than 80 will be greater than 80 will be 4%. Not 4%. What I have, it's 8%, because I will need to let me write it down. So for this, it would be 4%. Yes, that's right. Okay, and but if I want to include we have 1 minus delta is 5%. So now we have an issue, right? We are trying to average for 5%, but if I directly apply definition 8, I only average over 4%. I need to get additional 1%. So now let's see how we distribute. So I want 5%. Okay, then what I can do is I need to add back 1%. Okay, this will be exactly this VAR. Okay, of course I also have 80, and the probability is 2%, and I also have 100, probability is 2%. So those three numbers, okay, with probability 1%, 2%, 2% will give me exactly 5% tail. So now if I want to do averaging, what I have is 80, so it will be 1/5 plus 90, 2/5 plus 100, 2/5, right? So this is conditional expectation. So it will be 1/5% over the probability of condition, right? So you can easily solve. This is also 92. Actually, this is exactly what you get, right? So what you have is here is 1%. 1% over 5% is 1/5, right? 1/5. Here you have 2% over 5% is 2/5. So they are actually identical. So now I have good news because those two definitions are going to give me the same number, right? You should try to compute the rest. Let me give you the result. Right, for instance, for 96%, this is nice because it's fully used, right? And I can directly use this definition, 90, 2/4 plus 100, 2/4, meaning I'm using this definition. So I know it's 95 because I'm trying to do the average, right? And 96%, I have exactly number, achieving this number. So on the right-hand side, I will have exactly 4%, 2% from 90, 2% or from 100. I have exactly 4%. That's what I want. I want to average over 4%. So you can also do the rest too. to the number will be 100. Okay. Let's conclude this with a mathematical result. I think for you it's enough if you know that this is coherent. Previously, when we were discussing VAR, we know VAR is a good measure. It satisfies monotonicity. It satisfies translation invariance. It also satisfies positive homogeneity. TVaR will inherit all those properties. The reason it's simple is because TVaR is, by definition, is the average of VAR, right? And because it's the average, so it will hold the monotonicity. It will also hold the translation invariance. It will also hold the positive homogeneity, right? That is simply because of integrals, right? Those are the properties you have from integrals. So everything will stay. And on top of that, it will kill this. We know for VAR, subadditivity does not satisfy. That is well, to many, that is a huge issue, right? Because they argue that subadditivity is a very, very important axiom because that gives us the motivation to do diversification, to do merging in business, to do many things, right? It violates the subadditivity, so we want to come up with a different concept to overcome this drawback. And here, TVaR is a good candidate. It's closely related to VAR, and we claim subadditivity now is good for TVaR, but not for VAR. We will need to use this concept. It's actually very easy to prove. All you need to apply is Tao rule. So let's say you let's say you want to calculate this unconditional expectation. You can put condition, right, and then condition on it. So what do I condition? I condition on x bigger than c, and then I need to times by the probability that x greater than c. Then my next condition is, as you probably have already guessed, less than or equal to c. Then I need to times by x less than or equal to c. Right? Okay. This is very nice because I already know the result for the second one. Right? I'm taking expectation for the positive part. And if x is less than or equal to c, this is 0. So the whole thing is 0. So by the way, I think we used this property when we work with payment in a loss event and payment in a payment event, right? That's the identity we used. Okay. From here you directly see this because what is TVaR? TVaR is this. Okay. So that's what we have. I mean, TVaR is x greater than var, right? Well, you can break this x as x minus c plus c given var, given x greater than var, right? And then, of course, you can pick c to be var. Then this is exactly what you have done here. The next expression is more mathematical. We are not going to go to discuss this. That means it's a convex measure. We already know, right? Positive homogeneity plus convexity can actually imply subadditivity, which is what we see down here. But anyway, this is definitely not important to us. It's a much advanced topic. It's my entire point is to convince you that VAR is a coherent risk measure. In some sense, that makes it a better choice than VAR. That is the reason why TVaR is the current industrial standard. Of course, you could argue that it only considers the average, right? Right. VAR is a single point. TVaR, I missed A. TVaR is the average of all those points on the right tail. But is average the best measure you can think of? Right? Let's say if two random variables have the same mean, does that mean that they have the same risk? Probably not, right? So you may want to use higher moments. Like not only I want to know the average on the right tail, I want to know the average plus some of the variance, right? Because variance measures the fluctuation among the tails. So there could be generalizations, but so far we are happy with TVaR because it's really nice. It has all the best properties given this integral representation. So I guess that's everything I have for TVaR, and I believe that's already more than what we need for this course or the short-term actuarial mathematics. So if you feel challenging on some of the mathematical results, it's okay to skip. The most important thing is to calculate VAR and TVaR. So we already did continuous and discrete. Of course, I can give you more complicated examples. Actually, there are many exercises from the textbook, so you should try and do the computation. As long as you know how to compute, that's enough for this topic. Okay, I'm going to stop here and see you in the next video.